Welcome to the second part of the tutorial in which we will start using the simulator. So first of all, I prepared a sequence of increasingly complex examples, and you can find them at this URL on your screen. So please visit this website. You will find a GitHub repository. To import the code, my suggestion is to use Git, of course. So pop up a terminal. Here is mine. Go to the web browser, select code, then HTTPS, copy, and use this command, git clone, and paste. Now move inside the folder. In case you don't have Git installed, you can go back on GitHub, click code, and then download zip. It will download a compressed archive with the examples inside. You should unpack it and then pop up a terminal inside the folder. Let's take a look at the project structure. I prepared an easy to execute Gradle project, and in particular this is inside the src main YAML folder are the examples we are gonna see in this tutorial. Alchemist specifications are written in the YAML serialization file. YAML is a file format similar to JSON. I'm gonna show you the most prominent features in a text editor. You can use the text editor you prefer. I'm gonna use Visual Studio Code. So let me showcase the most important features of YAML based on the examples that we will analyze in detail shortly. Scalar types in YAML include integers, floating point numbers, and strings. Strings don't need to be surrounded by double quotes, but they can be. Comments begin with sharp. Mappings are key-value associations that can be written into formats. One is similar to JSON and is made by wrapping the mappings within curly brackets, separating its key value pair with a comma. The other doesn't require curly brackets, but keys can be separated by a new line, like in this case. Mappings of mappings are possible, again into formats. You can either write a key or a value which is a map by wrapping it in curly brackets, or you can simply indent, like in this case. Lists can be created into formats as well, either by separating the elements with a comma and wrapping them in square brackets, or by creating a list similar to Markdown, in which you put one element per line and prefix the element with a dash. There is also support for multi-line strings. For instance, in this case, for a multi-line string, you can first prefix greater than, and then write the string in the lines below. The indentation is automatically removed by the YAML interpreter. Besides a better readability, one of the reasons to prefer YAML to JSON or other formats is that it enables a form of code reuse, or don't repeat yourself. For instance, in this key, I associated the contents with the name by prefixing the name with an ampersand, and then I reused it here by referring it with a star. I will now show a minimal example of simulation by creating a new file and calling it example. The most minimal specification for the simulation is very compact. You just need to specify which incarnation you intend to use. So it's just incarnation and, for instance, Sapere. Let's see at the infrastructure with which we execute examples. Just a quick look. It's all written in this file build.gradle.kts. We will rely on Gradle to launch our application. I prefer this way with respect to a normal Java file, and the reason is that Gradle can automatically pull in dependencies from the internet if they are needed. In this case, we are using these modules of the simulator, the UI, incarnation Sapere and Protelis, and the overall general Alchemist module. How does it work? Basically, I wrote a custom task which searches in the src main YAML folder and for each file it creates a Gradle task that executes the simulator for us by passing the arguments. The arguments that are passed automatically are the, of course, the simulation file to execute, an export directory that we will see at the end of the tutorial, and it automatically loads an effects file if it exists with the same name of the simulation. If you look, there's a folder which is effects. Inside there are effects file. The Java Swing graphical interface of Alchemist is able to load them in such a way that if you find a pleasant graphical appearance for your simulation, you can save it. The task that is generated by this Gradle configuration has the same name of the simulation file, prefixed by the keyword run. Let's execute our minimal example. So I'm pulling up a terminal. To execute under Linux and Mac OS or any Unix is /gradle w run example. If you are on Windows, you should substitute /gradle w with gradlew.bat. It's a bat script, so that's the appearance of Windows. I'm using Linux right now, so I'm using /gradle w run example. You should see this graphical interface is white without nothing. In fact, we did not specify any deployment, we just required an empty Euclidean space to be created. Let's now see the first example of the tutorial. It's a very simple deployment. As you see, we load the incarnation as we did in the first example, but we have two new keys. One is network model, one is deployments. The deployments key contains the list of spatial configurations of devices in the environment. Under the network model key, we specify how nodes should be connected in the environment. It's basically the linking rule that we discussed in the first part of the tutorial. The Alchemist loading system is designed to be able to load arbitrary Java classes or Kotlin classes or Scala classes by specifying its type and parameters of the constructor. The simulator automatically fetches all the compatible subtypes for each category of elements, and if provided with this syntax, finds a suitable constructor, injects the parameters that are implicit. For instance, if an environment is required, you don't need to specify it manually inside the parameters list because it's implicitly specified inside the configuration file. How can a user know which are the available types? So the best way is to connect to the Alchemist website, which is alchemistsimulator.github.io. For instance, in our case, we need the network model. Network models are under the linking rule category. So if you search for linking rules, you find itunibo Alchemist model implementations linking rules. Those are all the available linking rules. In particularly, we used the connect within distance. As you can see here, there are constructors, and all the constructors are documented. In this case, the class only takes one parameter, which is the radius of connectivity. We also use deployments in point, so we can search for deployments, and these are all the available deployments. There are several of them. The one we used right now is point. As you can see, it takes 3 parameters, but one is the environment, which is injected automatically by the system. Let's execute this example. So pull up the terminal and then /gradle w 00 deployment in. You can actually shorten the name of the task by writing just run 00. If it's unambiguous, it will launch the correct simulation. The graphical interface pops up, and now we can see that there are 3 nodes inside the environment, the ones which we specified. By pressing L, you can display the links between nodes. A double click will open a tracker for the closest node. In this case, all nodes are empty. They have no content and no programs. The effects of the graphical interface can be regulated by clicking on those squares. Each one is an effect. There's an effect stack, so effects are rendered one after the other one in the order they are presented in the interface. For instance, if we want to add a red crown around those nodes, we can add an effect, type, draw shape, ask for it to be red, and then large. If we want the black one to be over the red, we can just move it on the left. The graphical interface supports pan by clicking and dragging, and zooming by using the mouse wheel. We now take a look at the second example, in which we create a Dodgeball program. So we enrich our nodes with contents and programs. As you can see, in this case, we have a single deployment, and the deployment includes multiple nodes. It's a grid. For each deployment, it is possible to specify a list of contents. Contents are usually specified by specifying a molecule and its concentration. With this incarnation, there is no need of specifying concentrations because molecules are actually tuple templates, but if they are ground, there is no need to specify which is the template they match. So the molecule can be injected without a specific concentration. In this case, we inject in every single node a molecule with two elements, a tuple with two elements. The first one is hit, it's a string, and the second one is 0. In this language, strings beginning with a lowercase letter are ground strings, and strings beginning with the uppercase letter are actually variables. Contents can be injected in every node as we did in this line, or the injection can be limited to a specific area in space. For instance, in this case, we limited it to a rectangle with these parameters. The behavior of the nodes of a deployment is specified in the programs section. In this case, we specify two programs, this one and this one. In the first one, if you see, the syntax of this incarnation is similar to applying chemical reactions to tuples. So we say if some node has a ball and the node has been hit n times, then delete the ball, which doesn't figure on the right-hand side of the reaction, create a new molecule which is launching, and count a hit. The second rule says if the node is launching the ball, then send the ball to one neighbor randomly. One neighbor randomly in this language is the plus. To send something to every neighbor, you can use star. As you can see, in this case, the program has also another descriptor, which is time distribution. Time distributions are used to regulate how quickly programs should be triggered if their conditions matched. In this incarnation, if time distribution are unspecified, the reaction is intended to be scheduled as soon as possible. So as soon as the condition is valid, then the program is executed. In the first reaction, instead, we limited the maximum frequency at which it can be executed, and the reason is that if both those reactions were executed as soon as possible, since one of them is always executable, the simulator will never get past time 0 and will continue to schedule event at the initial time. Let's now execute the Dodgeball program. Usual ./gradle w run 01. A network of devices pops up. Black nodes have the ball. If we run the simulation by pressing P, we see that now balls are traveling around the system. Also, we change the color of nodes based on the number of hits. There's an effect that does that, is this one. And as you can see, nodes in the center of the scenario get hit more frequently than those in the corners and borders. That's quite expected. The air button synchronizes the simulation to runtime, or tries to. You can accelerate or decelerate using the right arrow to accelerate and left arrow to decelerate. This is valid both in the real-time mode and normal mode. We take now a look to the third example, in which we complicate a little bit the program and create a gradient structure in our grid network. So we get the same network model and the same grid deployment. We inject in a small area of space, the same area in which we had the balls of the previous example, a molecule called source. Then our program says, if I am a source, then I still am a source, and I generate a gradient with distance 0. We run this molecule creation at most once every 10 seconds. The second reaction is executed with an average frequency of 1/100, and it says if I have a gradient with some value, then I keep that value and propagate to my neighbors the fact that they are at distance at the distance I was +1. The variables matches on the left-hand side can be reused on the right-hand side. The third program cleans up multiple gradients by saying that if I have a gradient with some value and another gradient with a higher value, I only keep the former. Finally, the third reaction ages the information of the gradient. The reason is that if we don't forget the fact that we were at some point with the sum value of the gradient, we won't ever accept that the values grow. They could only get lower and lower. Finally, if our gradient gets higher than 30, we interpret this as, okay, we are probably disconnected from the rest of the network, and we just delete the gradient from the node. The gradient is a distributed data structure which is at the basis of many other distributed algorithms. We now exercise the example by running /gradlew run 02. We press P to start the simulation, and as you can see, nodes get colored depending on their distance from the sources. As you can see, some nodes flicker their color. This is due to the artificial aging of the information process. We can play with the nodes in this scenario a little bit by selecting them and moving them where the simulation is running. This is done by pressing the S button to enter select mode. They get selected in blue, and they can be moved, for instance, by pressing the O button. They can be moved around the scenario, and once they are dropped, the network gets rebuilt. We can isolate some nodes. As you can see, the gradient is very slow at adjusting in a pejorative direction, because the network adjusts at the speed of the node that is slower to decay its information. On the other hand, if we move the source, the gradient is very, very fast at adjusting in the lower direction. This issue is typical of algorithms concocted with a language which is not at the correct level of abstraction for what we want to express. Alchemist is in fact able to simulate examples by using more expressive languages such as Protelis and Scaffi that rely on the paradigm of aggregate computing. We will see them later, and we will also have an example of gradient which stabilizes much better. Before getting to aggregate computing, I want to show you an example of advanced deployments. Right now we only seen deployment in points and deployment in grids, but there are many other deployments. One of the most interesting are the deployments that use the GraphStream library to generate networks. In particular, in this example, we generate 3 graphs. Each one features 300 nodes. They are located one aside the other one. Information on the specific graph is extracted by the specific GraphStream implementation of the graph, and these parameters are fed back to the GraphStream implementation. We can launch it as we launched the other examples. Run 03. There is no program in these deployments, so there is nothing to run. It's just to showcase how the simulator can be used to generate complex scenarios. I'm showing links, and of course I can create larger nodes.